Okay, I'm going to try something new, which is a video narration of my blog post. In this post, I created a extension for SingleStore that used Google's RE2 regular expression library to add some new regex related functionality to SingleStore. But really, this blog post is about how easy it is to extend the database now using any language that can be compiled to WebAssembly, which is great because at least I think SQL is really awkward for doing things like transforming strings and transforming blobs and that sort of thing. So being able to use a more general purpose language is just much nicer. So before we get into how I created this extension, I just want to show it off a little bit. So it's available, linked here on GitHub, and it's really easy to install. You can just copy paste this into any SingleStore. I have here my instance of SingleStore in the customer portal where I have inserted a bunch of data that's like URLs, random URLs. I added some random stuff. So there's a whole bunch of unique fake URLs in this database. And we can see that there's like 300,000. So say I wanted to find ones that were GitHub URLs only and count those. I can use this built-in regular expression here, and it will run, and it took, you can see 430 milliseconds, counted about 100,000 GitHub-based URLs. But say I wanted to go from here to extract the GitHub usernames and count how many URLs have how many GitHub, how many URLs contain which GitHub usernames. So that might be a little tricky to write with SQL. Let's try the new extension. So all I'm going to do is copy this and paste it in and execute these statements. This first one, create extension, is the actual extension. It goes and gets the release of this extension from GitHub and installs it in the database in a safe way because it's WebAssembly. It can't really do anything to the database. It's hosted within a sandbox. These two functions below are wrappers. This makes it easier to version the extension so that I can upgrade it later without needing to break my queries during the upgrade after I drop the old one and install the new one. So let's execute those. And that's it. That was all that was required to extend my database with the RE2 functionality. So let's try to get the same thing that I just did using the S2RE2 match function with the same pattern. I can execute that, and it got the same result. The first one was a compilation. It actually turns out that with this particular pattern, and some patterns are like this, some patterns aren't, this is faster to use the STRE2, the RE2 library, than it is with the built-in regular expression library, which you'll find with some types of patterns. The nice thing that RE2 does is guarantee linear performance regardless of the complexity of the input or if you have it from an untrusted source or a possibly malicious source, it'll still run in linear time and won't explode. And here's another function, RE2 match extract, which makes it very easy I can just throw parentheses over the part of the function that I want to extract and extract that out as the GitHub user and then group by those. So we can see that looks like there are, because this was generated data, 65,000 references to Scripting core user, 65,000 references to my own GitHub account there. So that is an example of what this extension that I did does. Regex is useful. It might be a little niche for this particular extension, but the whole point was actually how easy it was to install, what you just saw, and create that extension. So let's go ahead and go into what it took to create it. So I just covered this sort of stuff. I'm going to upload this video later in that spot, so we'll see if I can actually get it recorded to the end. Okay, so it was pretty easy to create this extension. For prereqs, all I needed was Docker, and I used Windows Subsystem for Linux because I have a Windows machine, and that was about it. I just did the build of all the libraries in the Docker container, extracted the generated WebAssembly files out, which I'll show in a bit. But let's back up a bit and talk about what exactly we're building. So a single store WebAssembly function is based on an early version of the WASI canonical ABI, which is WASI is like a standard way to have WebAssembly functions hosted within some environment, so that regardless of what language they're written in, or regardless of the host implementation, there's like a defined way for them to talk to each other. And Single Store uses that for their WebAssembly UDFs. It's an early version, and this has been evolving very rapidly. So it's maybe a bit different from like the current latest WASI interface, but it's pretty straightforward and it's pretty easy to write to. So in order to create a WebAssembly UDF, like the ones I did for RE2 wrappers, you can optionally create an initialize function, which will be called before anything else is called within your WebAssembly module. You have to implement some memory management functions, so the host can allocate memory within the module, and then free memory if it's working with something dynamic like strings and whatnot. And then you have to implement export your actual functions that you want to expose. So there's an interface for these function calls. There's a tool that generates bindings for this interface. It's called WIT-BindGen, and it does a pretty good job. If you write an intermediate language called WIT, it will generate bindings in C or Go or other languages for you. Since single stores UDFs are based on an earlier version, it's hard to get WIT-BindGen to generate the correct types of functions or the correct function names. The parameter passing is pretty much the same, but things like this realloc and free are different. And since the contract is actually pretty simple anyway, I tend to just avoid writing the WIT files and using WIT-BindGen and just write the parameter passing code kind of directly. So we will get into that in a second. Let's see. So here's an example of, it's pretty straightforward. If you want to expose a function with this interface, it takes an integer, a big int, and returns an int. And you notice these are all not nulls because WebAssembly has no defined mapping, or the WASI specification has no defined mapping for SQL null, so everything has to be not null when passed to a WebAssembly function. This will just get mapped to an int is int 32, a big int is an int 64, and it returns an int, which is another int 32. So when you're using primitive types like this, super easy to define the function in the right way within your C code, or C++ in this case. If you need to pass something like a string or another like dynamically sized data type, these get passed as a pointer to a allocated memory containing the value, and then the length of that value. So, and then on the return, if you want to return more than one value, in single store you can do that with a type called a record, which in this case we want to return a bool and a long blob. This long blob as well, just like the string, is going to need to take a pointer and then a length. So when a dynamic thing is passed in, the host will call the canonical ABI realloc function to allocate some memory in the WebAssembly module. It'll copy that string into that memory, and then it will call your function with the pointer and the length. So that's what you see here. That's pretty straightforward. On the return, if the return is anything that can't fit within a primitive type, the return value should be a pointer to a structure. In this case, I've defined it here, that contains all the values that you want to return. And in this case, because I'm returning a bool and a long blob, I get a bool. This should actually be a int32 underscore t. This is wrong here. I will correct that in the article because booleans are passed as 32-bit integers. And then the pointer and the length for that long blob. The host will then free the memory that's pointed to with this pointer. So you have to make sure that you allocate it with something that the host can call canonical ABI free on. And that's about it. If for all the things that you'd want to do from the database is probably related to strings, maybe long blobs, and these primitive types, that's about all you have to know about the parameter passing and the interface. So the cool thing is any language in which you can kind of express parameters in this way and compile to WebAssembly can be used as a UDF in SingleStore. I think the broader idea of WASI, the WASI effort, is that you can use them even beyond something like SingleStore. You can make these units of computation that can be used pretty much anywhere in all kinds of clouds that support WASI WebAssembly. But at least right now, it's really convenient to be able to plug anything into SingleStore and extend the functionality. Especially because there's lots of really cool libraries written for other languages, like C, C++, Rust, Golang, that it would be nice to just leverage the functionality of those directly within your database rather than set up a lot of extra services layered on top. Okay, so let's talk a bit about what it actually took to wrap Google's RE2 regular expression library. So RE2 is written in C++, so I chose to write the wrapper in C++ because it made sense. I created 3 files, mem.cpp for the memory functions, and then the function that actually contains our UDF wrappers, and then abs.cpp, which is kind of a dummy mutex, and I'll get into that later on. So mem.cpp, this is just the realloc and free functions. You can see that I had to get them to work and be exported from the module. I used extern C. I used this mscripton keep alive. I'm going to compile this with mscripton. You can also use the WASI SDK, but I found that mscripton is just easier to get things working when the libraries you're compiling depend especially on pthreads. In this case, the library had a dependency on pthread, didn't actually create any threads, but it used the synchronization primitives. So I had a hard time getting it to compile correctly with the WASI SDK, so I just used mscripton. And that seems to be a common trend for me, at least, to prefer mscripton and get better results with that. So that's what I've done here. So all this realloc function does is call the built-in realloc, or the standard realloc. And if it can't realloc, it just aborts. And the free function just calls free. So pretty straightforward. So the UDF implementations are in main.cpp. There's 2 functions that I'm exposing, match and match extract. And so these functions are in this file. I used the absale string view. RE2 depends on this library called absale, which has its own string view. So rather than bring in the std string view, I just decided to use the same one that it was already using to hopefully save on some binary size. Binary size is really important to keep it small. The bigger it is, the slower it is to initialize the function because it has to create the memory and copy all the code. So if you're creating it once and then running it over like 200 million rows or something, it doesn't really matter. But if you are doing like a very quick query that will just operate over a single row and run once, you can get better performance overall if you really focus on binary size. So I try to make the binary sizes as small as possible, and by avoiding bringing in extra libraries, that's a major way of doing that. In this case, I ended up with a binary size of about 180 kilobytes for this RE2 wrapper. So again, I bring in mscripton and RE2. Since in single store, it'll create an instance of your module. I think it's ends up being like per thread or something, but it generally will call it for many, many rows. It'll create it once, call initialize once, and then call your exposed function maybe 100,000, maybe a million times. And so it can be useful to cache things that would be computed in the same way on every call. And in this case, the RE2 library supports compiled regex. And so I've declared some global variables that remember what pattern was compiled and have an instance of the compiled regex. And this will improve performance. So let's look at the match function first. So the match function, I have an if-def here I'm going to compile this separately for each exported function just to, again, optimize the binary size. It doesn't help anything to have one module that exports lots of functions. There's no advantage to that within single store, so it's better to just compile a unique smaller module per function. In this case, I think it saved like 2 kilobytes or something useless like that, but in other cases it can be important in order to keep the binary size down. So again, I use mscript and keep alive to make sure I can export this extern C. Here's the parameter passing of a string coming in with the pointer and a length, and the pattern string with the pointer and the length. I create a string view over each of those. If I have previously created a compiled regex, but the pattern is different than before. So this might be the case if you are calling this function and the pattern is actually stored in the row in a different column and you're using that pattern against some constant value or something. In that case, the compiled regular expression doesn't work. We just use the uncompiled approach and return the result. And here it's our responsibility to free the memory of the pointers that are passed in. If that's not the case, if we either haven't compiled anything yet, we compile it, and we just save patterns, so we don't free it in this case. We only free it if we're not going to save it. Then we use the compiled version of RE2 and return the result. So hopefully this is where we end up spending most of our time, because this is the fastest function exposed by RE2 for matching. So that's the match function. That's all we needed. Match result was a little bit more complicated because we're returning more information. So I have to return whether or not it matched, and then the submatch or the capture group's pointer and length, because I'm returning the captured string. I have to return both of these because there's no nullability in the WebAssembly UDFs, like I mentioned. So in this case, like, is the empty string the thing that was captured, or does it mean there was no match? I didn't want there to be some ambiguity there, so I'll just explicitly say matched or no matched. And if it's matched, this will contain the captured string. Because we are returning more than one value, we declare just a global variable, and we'll return the address of that variable as our return value. Otherwise, this follows the exact same pattern. If we can't use the compiled version, we use partial match. In this case, we also pass in the thing to extract the capture group. And if there's no match, we just return no match with a null pointer, 0 length. If there is a match, in this case, we know that we're responsible for the incoming string's pointer now. We're supposed to free it. But since we know that the result that we want to return is at most the same length, we can just reuse that memory location to store the result. So we just copy the extracted match there and then return that. And that saves us a call to free and realloc, which is probably not worth anything, but I thought it was maybe might as well optimize. And again, the faster path using the compiled version is down here. So that's it. All the work for this was done by Google to make this cool library, and all I had to do was call it in a way that exposes the functions in the way that I want to call them from SQL. So that's all the code that was required to wrap RE2. Now let me talk a bit about the final function here. So abs.cpp, RE2 is, they make sure to say it's thread safe. You can use it for many threads. So they use something called an absale mutex. This depends on some debugging code, it depends on some time code, and it ends up pulling in about 30 kilobytes of extra libraries. Since WebAssembly is single-threaded, there are proposed ways that WebAssembly can be multi-threaded. I think some hosts have extensions for that. In our case, within single store, it's definitely single-threaded. The mutex is just pointless. So here, instead of linking in the actual absale mutex, I've just linked in one that's empty on all of its lock and unlock functions. And this saves 30 kilobytes in the generated library. Okay, so let's talk a bit about building this. So definitely the easiest way to build is just to build it in a sequence of steps in a Docker container, because Docker is automatically going to cache each step. So as soon as you get something working, you can kind of move beyond it. And it's just a really fast, efficient way to kind of go about getting things to build. So I picked a version of RE2. I picked a version of absale, which is the library RE2 depends on. I'm using the latest Emscripten SDK, and I get the CMake build essentials. And that's about all the prereqs. So the first thing I need to do is build absale. So I go ahead and clone it, and I make it with emcmake, which is Emscripten's version of CMake. I'm going to say, let's see, release cxx20, and then I'm passing this standalone wasm flag, which causes Emscripten to emit a WASI compatible binary, which is the sort of binary that we need for a single store. Let's see, turn off exceptions, turn off some other things, enable link time optimization. And then this is really important, disable absale logging. If you don't disable this, it brings in about like 100 kilobytes of like string formatting tools that just, the logging doesn't even work within our UDF. So it was just extra stuff that we didn't need. Luckily, the absale team made it very easy to just completely eliminate the logging by defining macros like this. I came up with this through a lot of trial and error and just like reading the docs on how to build absale. I think the important thing was that the CXX standard matches the one used for RE2, and that ended up being about it. So run emcmake and then run make install puts the headers where they need to go, and that's that. So the next step is building RE2. For this one, clone RE2, actually use the exact same arguments as for absale, and that was it. It just builds. So now it's time to compile our own wrappers. So we copy the code in. We pass our if-def, so we're actually going to compile the match function. And there's a few interesting things here. One is standalone wasm. That's the type we want to generate, like I mentioned. We're passing use em_malloc, which is a simpler malloc that's smaller. So again, it keeps the binary size low. This one is really cool. It's not fully utilized here, but it's a neat feature that is really useful for some of these UDFs. So eval constructors will, if you construct global objects within your WebAssembly module, Emscripten will actually, after it builds it, it will run it so that the constructors can evaluate, and then it will save the state after those constructors evaluate. So the advantage of that is if your globals take a while or do something expensive in the constructor, you only pay the price at compile time, and then at runtime it's just already done. It's already set up in the memory. So this is very powerful for something like, I didn't do it here, but you could imagine putting a specific regex pattern as a global instance of RE2, and then you'll compile that pattern like literally at compile time, and then at runtime it just uses the compiled regex. So that would be the absolute fastest way to run RE2. Another thing this could be useful for is if, and I'm thinking of doing this next, if there was a extension for JSON schema, you could compile an extension to validate a specific schema, and it would build all of the validation structures at compile time, and then at runtime it should be super fast to validate that JSON schema. So I think there's a lot of potential in eval constructors, and that's another reason I like to use Inscripton. Here we have to say which functions we export. We've done that. We link the libraries that we need. In this case, it's only a few, RE2, and then a few of the abcel libraries. And the same thing for match extract. And that's that. The last thing that I have in the Docker file is it's really important to notice what you're importing and exporting, because if you are not exporting the function that you want to call, that is not going to work. And if you import a bunch of extra stuff for some reason, like you brought in a library that brings in a bunch of code that doesn't exist within, it's not one of the WASI imports. It's like something that maybe Inscripton provides, but WASI doesn't. It will show up in your imports, and you'll kind of see, oh, it's bringing in all this weird time-related stuff. I should probably look to avoid trying to use that within my library. So I found this really useful to kind of prune down what code I was depending on. And so I just emit the imports and exports to a text file so you can look at it after the build. So that's the end of the Docker file. So what you do is you just build the Docker file and then create a temporary container with that file, copy out the generated WebAssembly and those import-export files that I mentioned, and there it is. So that build process using Docker like that, it lets you use whatever build environment you want, whatever tool you want. At the end, you just end up with a WebAssembly file, and you copy that back out, and you're done. So I found that to be a pretty effective workflow for creating this extension and other extensions. So now how do we package those WebAssembly files into an extension? Well, for the create extension command, which is the new, I guess it actually came out in 8.5, but I didn't hear about it until now. It uses a tar-based format, or not a tar-based format, literally a tar format. So you tar up the files that you want to include, and so that would be the match.wasm, the matchextract.wasm, and then you just write a script, an install script with the same name as the extension, and tar those all up together. So in this case, we're going to have 3 files. So in the install script, you create the actual SQL UDFs. So here I create the function for match.wasm. I just say from local in file, mention match.wasm using export match, which is what's exported from that WebAssembly file. And that's that here. Generally, I think extensions are going to have 2, WebAssembly-based extensions are probably going to have 2 functions. Here, I have one that's not able to handle nulls because WebAssembly can't handle nulls. And then I have a wrapper function that properly handles the nulls. So if you pass a null input or pattern, it just returns null. Otherwise, it returns what the actual implementation does. And same thing for match extract. It has, if the input or pattern is null, it returns null. Then it gets the record format as that output that I had mentioned, where M is whether it matched or not, and S is the submatch that it captured. So if it didn't match, it returns null. Otherwise, it returns the submatch. So generally having the raw WebAssembly function with a very small wrapper is what you're going to see. So those are just put into an installation file, packaged into a tar, and that's that. That let me do that create extension command with the link directly to GitHub. So versioning, let's see, I'll fix this before release, this trailing sentence here. What I think this is trying to say is when you create an extension, it adds some functions to your database. And say you have queries that depend on those functions. If you drop that extension, those queries are going to stop working for some time because the extension's gone. So say you want to upgrade. If there's a bug in my current version of the extension and I release a new version and you want to upgrade to that, how would you do that without breaking your in-progress queries? So there's a pretty straightforward way to do that, which is you create the extension to make versioned functions, and then you create wrapper functions to call them. So, and I think I need to fix this syntax too, which I'll do before I post this actual blog post. But basically I create some wrapper match functions that will call the versioned ones, and you do that with create or replace. So that way you can create the new versioned extension and then update the wrapper functions, and queries that depend on the wrapper functions will continue executing without ever breaking because the function doesn't exist. It will always exist. It will just be updated to call the newer version of the wrapper. So that's how I think the most flexible way of versioning extensions. You can also then easily roll back to a prior version of an extension. This RE2 extension is very simple, so probably not going to need to do that. It might not even ever have another version. But for more complicated extensions, maybe it might be more important to be able to upgrade them to a new version or downgrade them if that upgrade doesn't turn out. So some closing thoughts here. So I am really excited about these create extension things. I think we can have a whole community of provided extensions that add useful functionality to the single store database. I wonder if this is going to become a way that other databases can extend their functionality as well. I saw Postgres had an extension that lets you use WebAssembly, but that was it didn't seem to be updated in a while, so I don't know where that one's going. But I think that in general, SQL, like I mentioned before, maybe it's just my bias, but I am not a fan of using it for basically manipulating data. Like if you want to transform strings, if you want to transform blobs, working with binary data can be kind of miserable in SQL. And in those cases, it would be really nice to use just whatever language was best for the job. WebAssembly gives you that ability, and it's super easy to install them using the create extension command. I think, let's see, I already mentioned about the eval constructors thing, so again, I'll highlight, I think that's really cool, and I'm going to try that out with some compiled JSON schemas. And another thing is this extension here, the purpose was to wrap a really cool library. Like Google RE2, really awesome library, let's just use it. And we can, thanks to WebAssembly. Another type of extension might be, what if you have the need for a UDF that just does like a bunch of string manipulation? Like say you have some custom format and you have to search for a delimiter and then go a certain number of characters forward and then extract that and then use that to find something else. It might be the kind of thing that, maybe it's a few lines of code in Golang, and in SQL, it would just be, maybe you ask ChatGPT and you try to have it help you, but it might be really hard to do in SQL. What if it was so easy to create these functions that your first thought was, oh, I'll just write it in Go and just add it to the database? So I think this create extension stuff gets it close. I'm going to try to do another post maybe on using TinyGo for that kind of purpose. So that's another kind of note here at the end. Anyway, thanks for sticking with me for my first video walkthrough of one of these blog posts. Try out the S2 RE2 extension. You can use it on single store free tier or any other instance of single store, the Docker container, it all works fine. And yeah, if you have any feedback, you can find the link on the blog, contact me on Twitter or whatnot. So thanks so much.